This is a practice exam for the second unit of the Process Dynamics and Control course. If you'd like to get this PDF, just come to the course website, APMonitor.com/PDC, and then on the right-hand side you'll see exams and projects. This is the second exam, and this is the closed loop control exam review with a list of topics and links, and then also the PDF to this exam. So you can follow along with this if you'd like a blank copy of the exam, and I'll also post this video there as well. So this is intended to be a 50-minute exam, and just some hints on getting more points is explain your solution method if you can't get all the way through it, make your work legible and easy to read, circle or box your final answer, and then pace yourself. Let's jump right into the first problem. This is a temperature control lab, and it's a hands-on lab where objective is to develop a transient model between the heater power and the temperature. The model is used to get initial PID tuning parameters for a controller. We'll have an energy balance to start with when the heater is adjusted between 0 and 1 watt, and we're going to say that this is 2 grams, and the heat capacity, overall heat capacity, is 500 joules per kilogram Kelvin, and the surface area is 5 centimeters squared, and the convective heat transfer coefficient is 10 watts per meter squared Kelvin, and we're going to assume that everything is at the same temperature. Okay, so here's a table of values. Right here they're given in SI units, so it'll simplify the unit conversions. We're going to start with this energy balance, then linearize it and get it into a first order linear system form. In this case we have 2 gains, one gain for the ambient temperature and the other gain for the heater value. We've defined some of these deviation variables where we just subtract the nominal condition for each of those. Okay, so let's jump right into this. Okay, so to linearize, we're going to put everything except the derivative on the right hand side. So I'll just move over the MC sub p for both terms. The next step is to just call this a function of temperature, temperature infinity, and Q. And this is the part of the function that we're going to be linearizing. So just to review that formula, if we have a function of 3 variables, that is going to approximately be equal to the nominal conditions. I'll put T naught, T infinity naught, and then Q naught. So we'll plug those in as the nominal conditions, and then we'll add in the derivative with respect to temperature. We'll plug in the nominal conditions. I'll just put X naught there, and then T minus T naught. And then for every additional term, we'll just add in the derivative with respect to that. If there are any variables left in that derivative, we'll just plug in the nominal condition, so that should be a constant. And then we'll do it for the final term as well. Okay, there's our linearized model, and if you had additional variables, you just take the partial derivative with respect to that variable, plug in the nominal conditions, and then multiply it by its deviation variable. So let's linearize this. We have the 3, I'll just call this one right there, I'll call that one alpha, this one I'll call beta, and this one I'll call gamma. Now if the nominal conditions are also steady state conditions, then we'll know that this term will go to 0. So the only thing we'll have left is dt equals alpha times temperature prime plus beta times temperature infinity prime plus gamma times q prime. That will be our linearized equation. So let's go get alpha first. This one, we just need to take the partial derivative with respect to temperature. So I'll just do that up here because there's the equation. I needed to divide by mc sub p, so I'll start with this one instead. Okay, the partial derivative of that with respect to temperature, we'll have alpha equals negative u a over mc sub p. Beta, if I take the derivative with respect to temperature, ambient temperature is just going to be UA divided by MC sub P, and then gamma is going to be equal to 1 divided by MC sub P. If I plug in the values in the table up above, that leads to an alpha value of negative 5 e to the minus 3. Yeah, it's negative 5 times 10 to the minus 3. And then beta is going to be 5 e to the minus 3. And then gamma is going to be equal to 1. Okay, so I could plug that into my equation down here below. But before I do that, let me get it into the standard form that I want, which is this form. So to do that, I just need to divide everything by negative alpha. So if I divide by negative alpha, then that's going to give me the form that you see up above. And that will be a negative. And this will also be a negative. Gamma divided by alpha times q prime. Okay, so we've got our model right there, and then if we just rearrange that, then and just recalculate it, we're going to have a value of tau p is going to be equal to 1 divided by alpha times negative 1, and so that's going to be equal to 200, and the time units on that are seconds. The kp1 is going to be beta divided by alpha, and that is going to be equal to 1, and the units on that are none. They're going to cancel out. And then finally we have gamma divided by alpha, and that is going to be equal to 200, and that will also, it's going to be K divided by W. Okay, Kelvin divided by watts. Okay, so there's our standard form. We just put this into a time constant form where this is going to be equal to tau p. This is going to be equal to kp1, and then this is going to be equal to kp2. So that tells us about how fast the system is going to respond and the gains for the different values. Now, the first one says if I have a 1 degree temperature change in the ambient conditions, then I'm going to have a 1 degree change in the temperature of my device, and that makes sense. Okay, and then it says if I have a 1 watt change in my heater, then I'm going to have a 200 Kelvin change in my temperature sensor. So that might be a little bit too high, but we can verify that later with experimental values. Okay, so next we want to calculate ITA set point tracking, not IMC PI parameters, based on the gain and time constant information above. So there's a link here, or you can just go to the course website under the PI control, and that will give you some of the tuning parameters that you'll need. It has IMC but also ITAE. Okay, so we want to use the set point tracking for ITAE, and those are listed right here. So those are fairly straightforward formulas. You just need to basically plug them in, and you should come up with a KC value of 0.0456, and the units on that are going to be watts per Kelvin. It's always the inverse of the KP value. Okay, so this is the KP value that we needed for that because that's our heater gain instead of the KP1. So KP1, that's for any disturbances. So if you have any ambient temperature changes, we don't control that directly. We're going to control the heater value. And then the tau I value is going to work out to be about 195.7, and the time units on that are seconds. Okay, so you know, in this case, those actually, I guess I should have mentioned this. I should have put this in the problem, and I didn't. I'll change that in the PDF. One of the important things about this is if you have 0 dead time, then that KC value could go to infinity. Okay, and then you also have a dead time there. So for this case, you could, on ITAE, let's just assume that we have theta p equals 10 seconds. Okay, and then that leads to these values right here. And I'll fix that on the PDF that's online, just so you can have something that makes sense for the ITAE tuning correlations. Because if you don't have any dead times, then it suggests with ITAE that you'd have a very large gain for your controller. Okay, so I'll fix that, but just use theta p equals 10 seconds. Okay, and then if you did IMC, it would just be IMC would be KP or KC equals 1 divided by KP. This would be with moderate tuning, and then tau I equals tau p, and so that would be equal to 200 seconds. And if you had IMC, you just do 1 divided by 200, and that would be 0.05 watts per Kelvin. So using IMC tuning correlations, even with no dead time, you'd get something close to what ITAE says. Okay, let's go on down to the next one. We have a PI controller, has a following closed loop response, and we want to characterize the performance of that. So we have time on the x-axis, and then the response is on the y-axis. We want to first of all talk about some of these quantifiable performance measures of an underdamped system. This is one that has oscillations. The rise time is going to be where it first crosses, the time that takes it, where it first crosses the set point. So the set point goes up, and at time 5, and then it first crosses at about time 9. So we'd say the rise time for that is going to be 4 seconds. The peak time is where it reaches the first maximum or minimum. In this case, this happens right here, right about 12.5. And so we'd say that the peak time, you guys subtract off the time from when the set point started, the peak time would be 7.5 seconds. Okay, the next one is the overshoot ratio. I'm just going to label some things on this plot. I'm going to call this distance right here A, The distance of the set point change I'll call B, and then the second peak I'm going to call that C. So the overshoot ratio is defined as A divided by B. How far you went over the set point divided by the set point change. And so in this case, A is going to be 0.5 and the set point change is 1. So the overshoot ratio is 0.5, or you could say 50%. The decay ratio is going to be C divided by A, and it's not the height of that one, it's the ones that are on the same side of the oscillation. It's how far it decays for each 2 pi cycle of the response. Okay, in that case it's about 0.1 divided by 0.5, and so we'd say that the decay ratio is about 0.2. Okay, so let's suppose that the objective is to limit the overshoot ratio to 0.1. So it's a little bit high right there, 0.5. We want to decrease that to 0.1. What changes would you suggest to the PID tuning constants, Kc, tau I, and tau d? Circle 1 for each. So if we want to have less oscillation, we generally want to decrease our Kc value. Now if we want to also make this less aggressive, we would increase our tau I value. Because in the PID equation, we're going to have Kc times the air plus Kc divided by tau I times the integral of the air minus Kc tau d times the derivative of the PV. So if we increase that, then it means that this whole term right here is going to get smaller. Okay, so we would want to increase tau I. And then tau d, we would want to increase tau d because this works to decrease oscillations. It decreases the aggressiveness of the controller. As you increase Kc, it has a penalty for any rate of change. So it tries to stop a fast rate of change. Okay, so the other question we have on this is this controller reverse or direct acting? So reverse acting controller means that the Kc is positive for reverse acting, and then the Kc and the Kp would be negative for direct acting. And often in industrial control systems, you'll see that Kc is always positive, but then you have an option to say reverse or direct acting, and that's the sign. So for this system, we're not really given the direction of the controller output. We don't see that on this, so we really can't tell if the gain is positive or negative. So in this case, it would be undetermined. Let's go on to the next one. This is a first order linear system that takes 5 minutes for the process response to get to 50%, not 63.2 as we talked about in the class, which is a typical measure that we use for one time constant, but it's 50% of the way to the final value after a step change of 3 in the input. The dead time, theta p, is 2 minutes, and the process gain Kp is 10 in the linear first order equation. This is a review for those who didn't get it before. Let's just go ahead and sketch this out. I know there's some equations here, but I think it helps to draw a picture of what we're doing. So we have an input change, and I'll just label this as, let's see, this one is going to be 1, 2, 3, and then after a certain period of time, I'll just say 5 seconds into it, we had a step change of 3. Okay, there's my step input of 3. And then the response is information on that response is given here. And so I'll just write out the 1, 2, 3, 4, 5. And then we expect nothing to happen for 2 seconds. And then 3 seconds later, it's going to get halfway there. So let's think about how far it's going to go in the end. We had a gain, a KP equal to 10. So my delta Y equals KP times delta U. My delta U is 3, so my delta Y is eventually going to go to 30. My delta U at steady state was 3. Okay, so this means it's eventually going to make it all the way up to a value of 30. And we know that it's going to get 50% of the way there, which is to a value of 15 after the 2 seconds of dead time and then the 2 minutes of dead time and then the additional 3 minutes that it takes to get 50% of the way there. So it's going to look something like this. There's our 2 minutes of dead time, and then it's going to come up, and that value is going to be 15. It's eventually going to track up to the new steady state value of 30. So we want to try to get the process time constant for this system. So let's see if we can write out the formula and use those to be able to calculate the time constant. Okay, so this was 3 minutes after, and that was to get to 50% of the way there. We know that to get 63% of the way there, that's going to be 18.9, and this is going to be the time constant, and that is going to be the dead time. So let's go ahead and use our formula. Let's start with this one right here, which is the explicit solution for a system with dead time for a step input. Okay, so we know that this y value at 50%, this y of t, is going to be equal to 15. It's halfway there. And then we have Kp times delta U. And we know that is going to be equal to 30. So let me just put in 30. And then I'll have 1 minus e to the minus and then t minus theta p. We know that's going to happen at 5 minutes minus 2 minutes divided by tau p. And then this s term there, that just says after theta p time that s goes to 1. So this is just going to be a 1 at the end. So I have a formula here that says I made it 50% of the way there. I just did 15 divided by 30 equals 1 minus e to the minus 3 over tau p. Now I just need to solve for tau p. So I can rearrange that. And this is going to be equal to negative 0.5 equals negative e to the minus 3 over tau p. And I'll just multiply by negative 1 on both sides. Take the natural log of both sides. So I'll have natural log of 0.5 equals negative 3 over tau p. And then tau p is going to be equal to negative 3 over natural log of 0.5. And that's going to work out to be equal to 4.33 minutes. Okay, so there's our time constant. So it was after 3 minutes after the dead time that we got to 50% of the way there. And then to get to 18.9 or 63% of the way there, it took an additional 1.33 minutes. And that's our time constant. Okay, so let's go on to the next one. Here we have a valve problem. We're trying to size a valve and determine its characteristics as an installed valve in the system and a pump. So we have a cool fluid flowing through a jacketed reactor. That's our system, and it's controlled by a valve. The cooling fluid rate is through a pump, and it obeys the following relationship. So this pump always produces 10 bar of head. Okay, the pressure drop is across the system and also across the valve. So the system pressure drop is going to be delta P across the system is going to be 0.1 Q squared. And that's going to be in bar. And this is delta pressure on the pump. And that equals 10 bar. And the relationship for the valve that you learned in this class was the volumetric flow rate equals CV times a lift coefficient times the square root of delta P across the valve divided by the specific gravity of the fluid. Now we're going to use a linear valve where F of L equals L, and our specific gravity is going to be equal to 1. So I can rearrange this equation to get the delta P across the valve. And the reason why that's important is because we have delta P for the pump. That's going to be the head that we generate is going to be equal to the delta P that we lose across the valve plus the delta P that we lose across our system. So it's a closed system, so we know that anything that's generated by the pump has got to be dissipated by one of these two. Let's just rearrange this one, and we're just going to basically rearrange it to get delta P of the valve on one side of it. Okay, so to do that, let's divide over, I have Q, and then we'll divide over the CV. We'll substitute in just the L because it's a linear valve, and we'll square all of that to come up with delta P of valve divided by specific gravity. And just multiply over the specific gravity to get the delta P across the valve equals Q squared over CV squared times L squared times GS. Okay, let's put all that together. We have these three, basically this relationship up above. We're just going to plug in the delta P for each of those units into that correlation. So we have 10 equals, and then the delta P across the valve is going to be Q squared divided by CV squared times L squared. And then specific gravity is just going to be equal to 1. And then we add in 0.1 times Q squared. Okay, so there's our relationship. If you wanted to, collect the Q's all on one side, you'd factor out the Q and then divide it over and then take a square root. And so Q would be equal to 10 divided by 1 over CV squared L squared plus 0.1. Okay, so there's our relationship of Q versus lift. One of the things we could do is just generate a plot of that and figure out the relationship of lift of our valve stem versus the flow rate through our system. So this is going to be important because we want to have as much as possible a linear profile between the two, because then we can come up with one set of PID tuning parameters that can be used to control the flow. Okay, we have the steady state is designed to be 4 meters cubed per minute when the valve is 90% open. We need to determine the size of the valve, and we primarily do that through the CV value. Units for CV are set to whatever makes the correlation consistent because it is an empirical parameter. So basically don't worry about the units for the CV as long as you're always using the same units for the other things in that correlation. So let's plug that into, I'm just going to start with this one right here and plug in some of those values. So I have 10 equals, and then the Q is going to be equal to 4. And so that's going to be 4 squared is 16. And then I have CV squared. My lift is 0.9. And then I'll square that. And then I'll add 0.1 times 16. So now I just need to solve for the CV value. Okay, so that's going to be 16 divided by CV squared times 0.81 equals 10 minus 1.6. And when I solve it all out, it's going to be CV is equal to 1.533. Let's just generate this plot right here just to show this so we could see how the CV value affects the flow through our system. We typically want to design our valve so that will be 1/4 to 1/3 of the total pressure drop is going to be across the valve when we're at normal operating conditions. So if we have a CV that's too large, it means we've oversized our valve, probably paid a little bit too much for the valve, but it also might be more difficult to do fine control of the flow. If it's too small, that means that the pressure drop across the valve is probably too large. You're going to be operating at 90 to 100% open most of the time, and a lot of the pressure drop is going to be across the valve instead of, and you're going to be using up a lot of extra utility costs to be able to pump that fluid through this circuit. So coming up with the right CV value is important to have good valve sizing. It's easier to change the valve trim later, but not the CV, the body of the valve. That can be much more expensive to change later. So I'm going to open up Excel and just implement this equation in Excel, and we will see how things change as we change some of the things like the CV or the lift for our system. Okay, so here is the Excel sheet, and what I'll do is just come up with, put this over to the side so we can still see it, and then I'll just come up with a CV value, and I'll just say that's going to be equal to 1. And then I'll have a column here for lift, and we'll just start off 0, 0.1, and then I'll fill this down, just drag this little box on the right down until you get down to 1. So we want to go between 0 and 1, and then this is going to be our flow, our Q value. So if I implement this formula that's right, let's see, there it is. Okay, you're going to have a divide by 0 if you leave it in this form, so just multiply the numerator and denominator by L squared CV squared, and let's implement that instead. Okay, so it's going to be equal to square root, and then inside that square root I'm going to have 10 times, and then I'll do CV, and I need to put a static reference there, and I'll square it, and I'll put the lift up there as well. Okay, lift, and I'll square that. Don't do a static reference there so I can fill it down. And then I'll divide by 1 plus 0.1 times, and then these same two values that I had. Okay, I think I forgot a parenthesis there. Let's see if that one fixed it. Okay, that looks good. I'm going to just double click here, and you can see the flow through that. Let's plot this, just lift versus flow. I'll insert a scatter plot and make this just a little bit bigger, move it over to the side. Okay, so when I had, if I had a large valve, let me put 5 in there. You can see that I can get up to flow rates, about 9 or so. If I have a very small valve, 0.1, then it's going to be, limit my flow to about 0.3. Okay, so this is also important for maximum flow through your valve. But in this case, I had a design condition here. It says when it's 90% open, it needs to be 4 meters cubed per minute. So let's use this 1.533 and just check that it at 90% it's going to be flowing at the right amount. Okay, so there you can see there is 4 right there, and let's just look at the profile to see if it's fairly linear for flow versus the lift, and it looks to be fairly linear, a little bit of curvature up there. If you had a larger, okay, this one would be a larger one, like let's go up to 10, then you'd see a very nonlinear profile. So you might want to use an equal percentage valve trim for your valve, okay, to make that more linear here. Okay, so that's it for the valve problem as well. There's going to be design conditions you're going to be given, and you have to come up with both the valve sizing, like the CV, as well as the valve trim type. And the two most common ones are the linear valves, but even more common than that would be an equal percentage valve. And so you should know about that as well, where F of L equals R to the L minus 1, and R is typically going to be between 50 and 20. That's just due to the type of trim you use for the valve. So you could use either one. You could use an equal percentage, or you could use a linear valve. Okay, so that concludes this exam review. So let's just review what we've covered so far. We did a first principles derivation to come up with PID tuning parameters. We did that for this temperature control lab, and using a fundamental energy balance, we came up with a gain and a time constant, and then that helped us come up with PID tuning parameters. We looked at the ITAE, but also the IMC tuning parameters, and also to submit that correction to the exam. The next thing we did is quantify the closed loop controller response, looking at things like rise time, peak time, overshoot ratio, and decay ratio. There's others as well, such as settling time, that you can use to quantify the performance. Talked about controller tuning and whether the controller is reverse or direct acting. We reviewed our equation that we typically use for a process system modeling, which is first order plus dead time, and then answered a question. This might come from something like talking to an operator where he's not, or he or she is not necessarily going to know how long did it take to get 63% of the way there after a step change, but you might ask him or her, how long does it take to get halfway there? And then you could translate that into a time constant. For the final one, we did a valve sizing, coming up with the CV value and the correlation that we need between the lift and the flow.